Okay, so in the previous lecture, we developed an efficient circuit for the quantum Fourier transform. I've just reproduced it for your reference. So now in this lecture, we are going to study the application of quantum Fourier transform. So this was the circuit. I have an input of uh, qubits or the quantum state J in its binary representation, and I get I get the desired output which was required. So once I have the quantum Fourier transform, so essentially what this circuit is doing is taking J and quantum Fourier transform, and it's essentially giving us, as we had seen in the definition of quantum Fourier transform, which also, by the way, in the binary representation is this guy. So now we have the QFT, the quantum Fourier transform. This is exactly this guy. So now we have the quantum Fourier transform. How do we use it? So one way we use it is the phase estimation algorithm. In some sense, you have seen this concept of phase estimation when we did quantum metrology. Remember, the deviation we wanted to measure was encoded as a phase, and we were estimating the phase through interferometry or something. Also, if you remember the midsem problem, uh, the circuit would be analogous to this. The midsem problem, which was the DQC algorithm, where we had a estimation, trace estimation. So the quantum circuit was very similar to that. I'll come to that later, soon. Trace estimation. So what essentially is a phase estimation algorithm? I have a unitary, I have an eigenvector, and that gives me, let's say, some phase. The goal of the phase estimation algorithm is to find or estimate the phase. So what will be our assumption? The assumption will be that we will assume one can create U and also apply U square, Un, all the powers of U. So here is a schematic what essentially we are trying to do. I have a state 0 going through Hadamard, and then I have a control unitary. It only activates when it's going to run, and the input state over here is going to be the eigenvector. This was 0 eigenvector. So what do I have? The state over here is essentially this guy, and after application of the control unitary I have this guy. So in other words, what's happening is control U that's after the application of the control U, and which gives me basically this guy. So that's the schematic for estimating the trace. Once I have the state, the phase information has come in the upper part of the circuit, and now the idea is to estimate this particular thing. So remember I was talking about the midsem. Over here we sent in the midsem we sent an identity operator over here, and that way we were able to estimate the trace. That was the DQC algorithm. But let's look at this thing. How do we estimate the trace? So I'll give you the trace estimation circuit, sorry, the phase estimation circuit based upon this concept. So I start with T qubits. And I start with the eigenvector U, and I'm going to apply the powers. So on and so forth. And here I'm going to control these gates, which are the powers of the unitaries, get activated through a controlled operation. Over here. So as you can see, what's going to happen? What's the state of this qubit after the control unitary has been applied? As we saw over here using this technology, the state over here is 0 plus e to the power of 2 pi iota. Let me just call it phi, or 2 to the power of 0 phi is also phi 1. Essentially this was nothing but u, and we already seen that what happens to the state over here. Similarly, you can see the state over here. Let me write with a red pen. Once I have applied the control unitaries, the state over here is this guy, so on and so forth, and on the final qubit the state is this guy. So once again, the final state is up to normalization. This guy. So now suppose phi is nothing but then the state is if I write this guy phi as that, then in our decimal representation, what does my thing become? So I'll just copy this again over here. Then the final state becomes this guy. So this is how the information about this phase is encoded in the state. And now at this point, let's recall the quantum Fourier transformation. What is it doing? It is taking a state which we saw in the previous lecture. Quantum Fourier transform is nothing but as we saw, and then the final qubit. So just stare at these two expressions. If this guy gives this guy, then the inverse operation, the inverse Fourier transform, is going to give me this back again. So the entire information of this state, these bits, which was in the phases, through an inverse Fourier transform can be recovered over here. So if in my phase estimation algorithm, I had the information about the phase, this is exactly identical to this thing, this quantum Fourier transform circuit. So through an inverse Fourier transformation, I can get the information I need. So in other words, this guy through inverse operation, inverse quantum Fourier transform, will become phi 1, phi 2, phi t. So terrific. So by measuring the state in the computational basis, computational basis gives me the phase phi exactly. So this is fantastic. So all I need to do is to, at this point now, once I have the phase estimation circuit, once I have the phase estimation circuit, I run these bits through an inverse quantum Fourier transform, which is going to be exactly the same circuit, gates reversed, and that way I am going to get this guy. So this is how I estimate the phase related to this eigenvector, and remember, essentially the problem boiled down to estimating the trace of this unitary, not sorry, the trace, the phase of this unitary, this guy, and here's a circuit to estimate that. This circuit embedded with inverse quantum Fourier transform. So this is kind of fantastic. I have a quantum algorithm for phase estimation, and we use this algorithm. We used quantum Fourier transform for this thing, and we also used a DQC like circuit which you had in the mid-sim. Now in the next lecture we are going to study the applications of this phase estimation process. So the next lecture would be the applications of phase estimation.